Um, all right. So here in this lecture today, I have three things that I want to do. I want to finish yesterday's lecture about topological defects in solitons first. Then I want to make some quick comments about the Helfrich theory of membranes, as Robin Brunsma briefly introduced in his morning's lecture. I want to show you about how that's related to what I was doing with liquid crystals. Okay? And then third, I want to tell you about modulated phases of liquid crystals. Okay, so for these three things, I may need 3 hours. Sorry, Camille. All right. Right, first, for defects and solitons. Okay, so everything that I showed you yesterday had to do with a one-dimensional measuring surface. That is, you were checking things along a line. Right, so if you wanted to see about a topological defect with a singularity, you make a loop that is a one-dimensional contour, right, going around the defect and see how the director changes along that curved line, right? Or for a soliton, you could draw a straight line going right through the soliton and see what happens along that line. Okay, so that's all great. But it can be generalized, right? It doesn't have to be a one-dimensional measuring surface like that. There are more complicated situations that have a two-dimensional measuring surface or even a three-dimensional measuring surface. Okay, let me try to show you. Okay, so let's first think about a two-dimensional measuring surface, okay? And suppose our order parameter is a three-dimensional polar order that is represented by arrows, like these yellow arrows with one head pointing in any direction in three-dimensional space. Okay, so you can see, this is a picture. So if you don't look at the green sphere, you just look at the yellow arrows. Okay, this is some director field, right? There's a vector at every point as a function of x, y, and z. Okay, so now suppose we want to sample what's happening in this director field everywhere on the green sphere. Okay, so I put in a green sphere to be my measuring surface, all right? And I want to say what's the director at every point on this green sphere, okay? At every point, that maps onto some point in director space. Okay, the yellow sphere is the set of all possible unit vectors, okay? So if I look at this point, that maps onto a point like this, right? If I look at this point, it maps onto a point like that. Okay. This, if we look at a little patch of the sphere in real space, the director on that patch covers a little area over here on the in the set of all possible arrows. Okay. So if I look at the whole northern hemisphere over here, it covers almost the whole northern hemisphere over here, right? That the arrows all around the northern hemisphere there are different places in the northern hemisphere here. Okay. If I look at the southern hemisphere, I also get directors that map onto the northern hemisphere over there, right? So far, so good? Okay. So the same way that you can define a winding number for one dimensions, you can define a 2D generalization, which says, how do we cover all the possibilities in this target space, in this set of all possible vectors, okay? And so the northern hemisphere here covers approximately the northern hemisphere there. The southern hemisphere here covers approximately the northern hemisphere here, but in a negative sense. So the same way that with winding number you can go clockwise or counterclockwise, with covering an area, you can cover the area in a positive way or in a negative way. Okay? So here, those two kinds of coverage cancel out. Okay? So this is a picture that does not have any defect associated with this measuring surface. Okay? Inside of this measuring surface is defect-free. Okay? This complicated looking integral, this is how you count how many times you have covered the surface. The net positive coverage minus negative coverage is this integral. Okay. So this is an example where this integral comes out to be 0. There's 0 net coverage. What about in a picture like this one? Okay. In this top picture, the director is sticking outwards everywhere from the origin. Okay. So here, the director is pointing outwards. So in this picture, the northern hemisphere here covers the northern hemisphere there in a positive way. The southern hemisphere here covers the southern hemisphere there in a positive way. Okay? So the integral that I showed you on the previous slide comes out to be +1. There is a net positive coverage, right? That over here, all the vectors on this sphere cover all the possibilities over on that sphere exactly once in a positive way. Okay. So this is a kind of topological charge, but it is different from the topological charge that I told you about yesterday. The charge that I told you about yesterday is a winding number associated with loops. Okay? This is also a topological invariant. It is also something that's constrained to be an integer, but it's a different kind of charge. Okay? This kind of defect is sometimes called a hedgehog. Okay? It is named after this little animal, which has all its little spikes sticking out in all directions. Okay? So it's sometimes called a hedgehog or a radial hedgehog. This kind of charge might be called a hedgehog charge. Okay? Here is a picture of a different kind of defect, which is also characterized by a hedgehog charge. Right? So here you can see the arrows are pointing in along the z-axis, right? Down there, up there. And they're pointing out in the x direction and the y direction, right? Everywhere in the xy plane. So here, as you sample everything on the green sphere, you cover all the possibilities there, but in the negative way. So this kind of structure has a hedgehog charge of -1. Now, that is the story with defects characterized by a 2D measuring surface. Okay. But you remember, there's defects and then there's solitons, right? Defects are what you get if you have something that's enclosed by a measuring surface. Solitons are what you get if you have something that just lives on the measuring surface everywhere. You can also get solitons that are characterized by how you cover all the possibilities of the vector. Okay? So this is a picture of a three-dimensional polar order defined just as a function of x and y, right? Nothing depends on z, okay? So your whole universe is the xy plane, and the measuring surface is also the xy plane. When you integrate over the whole xy plane, you see this covers a little section of the possibilities, some of it in a positive way, some of it in a negative way. Your integral comes out to be 0. Okay? This has no solitons. Here, but here is a possibility that's different, okay? Here is a possibility where right at the middle you have the vector towards the North Pole. As you go outwards, you cover more and more orientations. And when you go out to infinity, you're pointing down towards the South Pole. Okay? This structure covers all the possible orientations of this vector, each possibility exactly once in the positive sense of coverage. Okay. So when you calculate the integral to see how it covers everything, the same integral for the hedgehog charge, you get n equals 1. Okay. This thing is called a skyrmion. Okay. This kind of structure is studied a lot in the theory of magnetism, right? That there are a lot of people now working on magnetic skyrmions, and at an APS meeting you'll probably see 50 talks about that sort of thing. Okay. This is another variation where everything is twisted, right? As you go, if you're right at the center, the vector is pointing vertically. As you go out, it tips over, but instead of tipping over like this to make splay, it tips over like that to make twist. Right. This is also a structure that has an integrated charge of +1. So this is another kind of skyrmion. So this sort of structure might form in a material that likes splay, which magnets sometimes do at a surface. This kind of structure might form in a material that likes twist, which could happen in chiral magnets. This is an example of a picture of an anti-skyrmion. And so if you had a skyrmion and an anti-skyrmion in the same xy plane, those integrals would cancel out. Okay. So this is scaling up all the stuff I showed you with solitons to two-dimensional measuring, not just one-dimensional measuring. Here are analogous things in liquid crystals, right? So if you have pneumatic order, as you recall, the pneumatic order has equal populations pointing in the two directions along some axis. So you wouldn't represent the orientation by an arrow, you would represent it by a double-headed arrow, or maybe a zero-headed arrow, like that. Okay? So you can still make hedgehogs, right? So this is a hedgehog. This is a hyperbolic hedgehog. Right? This is a radial hedgehog. This is a hyperbolic hedgehog. They are both characterized by this integral for the hedgehog charge. The one awkward thing with pneumatics, though, is that n is equivalent to -n, and this thing that you're integrating is odd in n, right? It has 3 factors of n. So the overall sign is ambiguous, right? So here we can't say that it has a hedgehog charge of +1 or -1. You just say it's plus or minus 1. Likewise with skyrmions. You can have a skyrmion in a liquid crystal. This is a twisted structure, right? As you go outwards, the director is twisting the same all around the central core. And this is a structure that has a skyrmion number, this integral, which is plus or minus 1. The sign is ambiguous, but it is definitely not 0. So, like with the solitons I showed you yesterday, you can't get rid of this thing, right? If once you have a soliton, like a kink, right? A winding number, right? It's sort of stuck, right? You can try to push it to the edge to get rid of it, but you can't just make it disappear in the middle of the material without violating the boundary conditions or violating the continuity of the director. And the same with this. As a two-dimensional structure, it is stuck here and you can't just make it go away. I will skip that. There is a generalization. A question, please.
Yeah, with these like 3D defects, do they still add up the way that the 2D defects did? Like if you have like two, like because the sign is ambiguous.
Because the sign is ambiguous, the addition gets messed up. Yes. And so, because, yes, that's an excellent point. Because the sign is ambiguous, the addition gets messed up. And so if you have two near each other, you can't tell whether it's two pluses or a plus and a minus, right? And so the addition depends on other stuff, like if there's a disclination else somewhere in the material. And so it does get complicated that way, and the naive addition, like with electrical charges, breaks down. Yes. Please.
Doesn't there exist any solution to this problem of ambiguity, plus minus one, some other?
I mean, if you have just this with no disclinations anywhere in the system, okay, then you can just make an arbitrary choice everywhere and say, you know, right here I will pick that n is this and not that. And then I'll have to be consistent everywhere else, and I can be consistent everywhere else, and that takes care of the problem. However, if there is one disclination, or at least one disclination, anywhere in your material, then you can no longer make a consistent choice like that everywhere. And then the signs get messed up and the addition gets messed up. Okay, and thank you. Excellent points, both of you. The last thing I will mention is, if you thought a two-dimensional measuring surface was too easy, you can go to a three-dimensional measuring surface, okay? So that is possible, right? That you can have a three-dimensional measuring surface, and there is a topological invariant which talks about how you cover things as you look everywhere on a three-dimensional measuring surface, okay? Now, if you wanted to have defects associated with that charge, okay, well, you would need to be in a four-dimensional universe where the 3D surface can surround something, okay. We don't have that, okay. So instead, we just have solitons that are associated with it, right? So you can say, let the 3D measuring surface be the whole 3D geometry of a liquid crystal cell, and there are solitons that are characterized by that whole topological invariant. These things are called Hopfions, and the topological charge is called the Hopf index. And these are actually found experimentally, right? This is not just a theoretical construct. And especially a lot of these experiments have been done by this guy Ivan Smolyuk at the University of Colorado. And so I would refer you to his work if you want to learn about this kind of stuff. Okay, that is what I wanted to say about defects. Okay, any more defect-related questions? Please.
Yesterday we saw that we are not considering those defects which were occurring in 2D for 3D, where they go to zero, like while they evolve, they go to zero. So we say that they are not defects. We just ignore them, right?
Say a little bit more. I don't think I quite understand.
Yes. So for +1, I don't exactly remember was it
Mhm.
+1 or +1/2,
Mhm.
but there was a certain defect which was considered in 2D, but we just ignored them in.
Oh, yes. Okay, so that has to do with whether the director N is living in the two-dimensional plane or if it is free to rotate into the third dimension. Okay, if it is living in the two-dimensional plane, then you can have integer charge defects, right, where it sticks out around like this, okay? But if it is free to rotate into the third dimension, then everything that's sticking outwards like that can tip upwards. And then you can continuously transform what you thought was a defect into no defect.
Right. So
Mhm.
my question is, when they are having this defect, they do interact, right? For example, there are two defects.
Oh, if you had two such things, and then you're wondering whether they'll attract or repel, or that sort of thing.
Yeah.
Yeah. That's an interesting point. I mean, I guess as long as the director stays in two dimensions, then these things would attract or repel. But the director won't stay in two dimensions, not unless it's forced to. And so it will have a strong driving force that will make the director tip up into the third dimension and to get rid of the defects. And then you'll have to solve things numerically. There'll be a complicated evolution of the whole director field. It wouldn't be just described by the motion of two defects.
Okay.
All right, great, thank you. All right, the second thing that I wanted to talk about today was just a quick comment following up on what Robin Brunsma presented this morning. Okay, so you know this morning he was talking about the elasticity of fluid membranes, right, and was talking about how you get the Helfrich Hamiltonian, which is related to the curvature of the membrane. Okay, so I wanted to show you how that is related to the liquid crystal elasticity that I told you about a couple days ago. Okay, so because it's actually a very similar kind of consideration. All right, so you remember what I did 2 days ago with liquid crystal elasticity was starting with the idea that the thing that costs free energy is gradients of the director, right? That if the director is uniform everywhere, that's fine. There's no free energy associated with that, okay? But if the director is varying as a function of x, y, and z, that costs free energy, okay? So we can characterize it by a director gradient tensor with 6 components that looks like that, right? In the approximation that the director is almost vertical, okay? And then I wanted to break that down into 4 types of deformation, okay? And in that class 2 days ago, I broke it down like this, right? That there's a piece which is bend, a piece which is twist, a piece which is splay, and a piece which is this delta mode, okay? And this decomposition works in general, right? It doesn't depend on this assumption. In general, it has the mathematical form like this, but again, into a piece that's bend, twist, splay, and delta. Okay. What if we want to do the same kind of thing with a fluid membrane? Okay. In that situation, the thing that costs free energy is the curvature tensor of the membrane, right? If the membrane is flat, no problem, 0 free energy cost, okay? But if the membrane is curved, that costs free energy. In the approximation where the membrane is approximately flat, but with just little deviations up and down, okay? In that situation, we could describe it by, z equals a function h, the height function of x and y, okay? And then Robin showed you this morning that you get a curvature tensor, which is this tensor of second derivatives of h, right? You remember this from his presentation this morning. Okay. In general, right, you could define a curvature tensor for any shape of the membrane. You're not limited to situations where it's approximately flat. Okay? And so the curvature tensor will be some kind of 2 by 2 tensor. And in its principal coordinate system, that is its eigenframe, you can choose a coordinate system where it is diagonal, okay? And in that frame, it is 1 over r1, the first principal radius, and then 0, 0, 1 over r2, the second principal radius, okay? So this is the general expression for the curvature tensor, in its diagonal frame, with the principal radii r1 and r2. Okay, so now, like with the liquid crystal case, like with the pneumatic case, I want to break this tensor into 2 types of mathematical objects. Okay? This is a little bit simpler than the previous case because it's just a 2 by 2, not a 3 by 3. All right? So for a 2 by 2, it's already symmetric. So I can just break it into a trace and the traceless part. Okay. So the trace, the part with the trace times the identity looks like this. Okay. You can see that it is characterized by the mean curvature. Okay. So this is just the same construction that gives the splay over here. Right? That mean curvature means the same thing as splay. It means the normal to the membrane sticking outwards like this in all directions. Okay. Then the remaining part, like that, is a symmetric traceless tensor. Okay? And it is proportional to the difference of curvatures. The 1 over r1 minus 1 over r2. Okay? So there's a piece proportional to the sum, and there's a piece proportional to the difference. Okay? This difference piece is equivalent to the delta mode that I was talking about here, right? Because in the diagonal frame, that's just something here and then a negative something there. Okay. So far, so good? Yep. All right. Now, for the liquid crystal case, when I wanted to talk about the free energy density, please.
What happened to the Gaussian curvature?
Hold your horses. For liquid crystals, okay, the free energy density is a sum of the squares of the 4 modes. Okay? So something times splay squared, something times twist squared, etc. Okay? With the standard notation that I showed you a couple days ago, it's like this. Okay? And now, if I want to make that consistent with the standard notation, right, I can just rearrange the terms and say that a certain combination of delta and splay and twist is this total divergence, which people normally call the saddle splay. And so I get this standard form of splay squared plus twist squared plus bend squared minus this saddle splay business. And then this saddle splay business integrates to a surface term thanks to the divergence theorem, right? And so many people like to ignore it, even though maybe they shouldn't. Okay. What about with the fluid membranes? Okay. I've got 2 modes. So the free energy should be something times the first mode squared plus something times the second mode squared, right? So something times the sum of the curvatures squared plus something times the difference of the curvatures squared. Okay? So this is how I would like to write the elasticity of a fluid membrane. Okay. Now, if I want to rearrange terms, I can cleverly do some high school algebra here, where I multiply out these squares, okay, and then you can see that they look just the same, except that this one has a plus 2 over R1, R2, and this one has a minus 2 over R1, R2, okay? So I can combine them and have something left over that's proportional to 1 over R1, R2. This, in answer to your question, is the Gaussian curvature. Okay? What's more, this is what's quite correctly called the saddle splay. It's just like the saddle splay in the liquid crystal case, also known as the Gaussian curvature. And when you integrate it over all the surface, it integrates to some topological invariant, which is associated with the genus of the surface, with the number of holes in the surface. Okay? So if you are the kind of person who likes to neglect this term, you might also want to neglect that term. Okay? And if you're the kind of person who wants to think about this, then you might want to think about this also. Okay? So here, but I just wanted to point out, this is like the splay squared plus this extra thing proportional to Gaussian curvature. Okay? So that's the way I would perceive the Helfrich free energy. Question, please.
Can you explain a little bit more about the splay and the Gaussian? Because I think the first term it also includes the Gaussian, or it's just a printing mistake like 1 over R1 squared plus 1 over R2 squared.
Sure, it includes the Gaussian. You're thinking about the cross term here, right? Yeah. Sure. I mean, these things are all mathematically equivalent to each other. They're different ways of thinking about the same thing, right? And so you could say that the things you care about are the mean curvature and the Gaussian curvature, and that's what Helfrich did all these years ago, right? And so you get this expression for the free energy. Or you could say the things that you care about are the sum of the curvatures and the difference of the curvatures, right? And mathematically, those are exactly equivalent to each other, right? And the difference is a difference for the purpose of storytelling, right? If you want to tell a story about why does a membrane do something, you want to say, how do I tell a story about mean curvature and Gaussian curvature? Or how do I tell a story about curvature sum and curvature difference? Okay? And so there's no math that's going to tell you which is right or wrong. It's just a matter of thinking about individual problems and seeing which sort of story gives you more insight into that particular problem. Now, some of you who are listening to Dr. Brunsma very carefully may have noticed that there's one more term in the free energy that he showed, which is the spontaneous curvature. Okay? That is a thing I haven't told you about yet, but I'm about to tell you about that in the context of modulated liquid crystal phases, which is the subject of today's lecture, which I will now begin. Okay. Or shall we take our break? This is a break time. Okay. Go, quick. Take a break, whatever you need. I'll come back and start today.
you have time today or tomorrow to
Yeah.
discuss something about my ratios?
I have nothing but time. I have nothing after this lecture. on my
That's great.
schedule.
Thank you.
So yes, anytime, even just at dinner time. can be
Okay,
fine with
that's
me.
great. Thank you so
Good,
much.
good, sure. Yeah, chase him back in. It's okay. All right, let's resume here. Okay, so the last thing in general that I want to tell you guys about is what about liquid crystals that have some kind of favorable variation in the orientation of the molecules, a favorable variation in the director. Okay, so this actually happens, right? There are phases of liquid crystals where the director is not just uniform, but rather it tends to vary in some way. Okay, so I want to propose a kind of general ideology for how to think about all such variations. All right, so well, here I was just talking about this, right? About how I break down the elasticity into these four modes, and for bend, one thing that I want to emphasize is that the mathematical definition of bend is even in powers of n, right? It has 2 powers of n right there. Okay, so it doesn't matter whether I choose n or negative n, I get the same number for bend, right? That's great. Okay, likewise with twist. The mathematical definition of twist is also even in n, and so it also is invariant under the transformation of n to negative n. Okay, what about splay? Okay, well, I gave you a definition of splay that is a divergence of n, and you can see that it's odd in n, right? It has 1 power of n. And so if you change sign from n to negative n, then the splay changes from s to negative s. Okay, so if you wanted to construct an object, a splay-like object, which does not care about the sign of n versus negative n, no problem. You can do that by just taking s times n itself, right? That for sure has 2 powers of n, so it is invariant, okay? That's something I'm going to call a splay vector in contrast with the splay scalar up there, okay? And it's a splay vector, but it's a vector that is forced to be parallel to n, so it doesn't have freedom of direction. It's a vector along n. Okay, so that's for splay, okay? Likewise, for this delta mode, you can see the definition of the delta mode being this thing on the left minus this other stuff on the right. This is also odd in n. It changes sign if you go from n to negative n. But if I want to make something that is invariant under that symmetry, a change of sign between n and negative n, no problem. I'll just make a third rank tensor of the delta ij times nk, right? And that now is even in n. And so as long as I'm willing to deal with third rank tensors, I have everything that's invariant under this symmetry. So the third rank tensor is something which characterizes how this kind of tetrahedron that's embedded in the delta mode is oriented. It shows whether this tetrahedron is sticking outwards this way or anywhere in the xy plane. Okay, or in the plane perpendicular to n. So as a table, I can say I have these 4 deformations. Considering the symmetry between n and negative n, I can define the deformations this way, and they are 4 types of mathematical objects, right? Twist is a pseudoscalar, bend is a vector perpendicular to n, splay is a vector parallel to n, and the delta mode is a tensor of rank 3. Okay. Now, the next step in my ideology is to notice that each of these deformations is coupled to some kind of extra molecular order in addition to regular nematic order. Okay, let me illustrate that first with bend. Okay, so suppose you have molecules that are shaped like bananas, and these bananas make a regular nematic phase. In a regular nematic phase, there is orientational order along one axis, just one axis. Okay, so the bananas are oriented something like this. Their long axes are along z, and they're randomized in the plane perpendicular to z. You have equal populations pointing anywhere around like that. Okay, now suppose you apply a bend deformation to the director. Okay, so down here the director's aligned this way. I'll use my yardstick. Down here the director is aligned this way, and as you go up, it comes up like that. Okay, that's bend. Okay, that makes an anisotropic environment for the bananas. Okay, so the bananas will respond to that anisotropic environment by aligning like this. Okay, here's a mathematical argument, but it comes to basically the same story. Okay, now if these bananas are molecules with, atoms and bonds and stuff like that, right? Then they will probably each have an internal dipole moment. Okay? In this structure, all those dipole moments average to 0. Okay, so that there's 0 electrostatic polarization. In this structure, by contrast, the dipole moments don't average to 0. You'll have net order of whatever component of the dipole moment is pointing sideways along this banana axis, okay, perpendicular to the director. Okay? So you will see some net electrostatic polarization induced by bend. Okay? This really happens. This is called the flexoelectric effect, or more specifically, the bend flexoelectric effect. And it was discovered by Robert Meyer, I don't know, back in the 70s, based on symmetry considerations like this. And it's been studied in the lab for many years. Okay. So here we could say that you apply a bend. The bend is a vector perpendicular to the director, and you get an electrostatic polarization, which is also a vector perpendicular to the director. Right? So I'm saying a director deformation induces some extra molecular order with the same symmetry. What about splay? Suppose you have molecules that are shaped like pears here. Okay? In the ordinary nematic phase, half of them will be pointing up, half will be pointing down. If they have dipole moments, those dipole moments will average to 0. Now, suppose you apply a splay. Okay? That's this deformation here where the director is coming along like that. Okay? The splay makes an asymmetric environment for the pairs, and they will respond by aligning with respect to that environment. If they have a net dipole moment, if each molecule has a net dipole moment, then they will no longer average to 0, right? So you'll have some remaining electrostatic polarization parallel now to the director, pointing upwards. This is the splay flexoelectric effect, okay, where you apply a splay, you get a polarization parallel to the director. This was also predicted by Robert Meyer and also has been studied experimentally for many years. Okay. So once again, I would say the director deformation induces some extra order with the same symmetry as the deformation. Okay. So if this is true for 2 of the 4 modes, maybe you can guess what I'm going to do next, right? What about the other 2 modes? What happens if you apply those deformations? Okay. So suppose you apply a twist deformation, okay? Maybe you're starting with a system that has a random distribution of chiral conformers, right? So you have molecules. Maybe the molecules are not chiral the way an organic chemist would manufacture them, but they can adopt chiral conformations, right, which are different right-handed versus left-handed. If you put them in a twisted environment, then they'll respond to that. So you'll have more of the right-handed conformation and less of the left-handed conformation, or vice versa. Okay? So in that situation, you'll have some enantiomeric excess, a biased distribution. Okay? So in that sense, I would say, a twist, which is a pseudoscalar, could induce an enantiomeric excess, which is also a pseudoscalar. Okay? They both change sign under reflections. So again, I will say, the deformation induces extra order with the same symmetry. And finally, with this delta mode, this is now totally speculative on my part, but if you have molecules with this shape, like distorted tetrahedra, and initially you have just ordinary nematic order, so they're random in the xy plane, and then if you apply the delta deformation, then you'll tend to align those objects. And you'll get some extra orientational order characterized by an octopolar order parameter, that is a rank 3 tensor. So a rank 3 director deformation induces rank 3 molecular order. Okay, so that's flexoelectricity for the first 2 stories and kind of generalization of flexoelectricity for the second 2. So far, so good? All right. Question, please.
confused as to where is the curvature part in this. Are we talking about the like those banana structures you were talking, like single entities curved or whole assemblies curved?
Yeah, well, I mean, most molecules just have complicated shapes, right? And so they have some banana-like aspects of their shape and some pear-like aspects of their shape, okay? And so most molecules will have both the bend and splay flexoelectric effects, okay? So the bananas, the picture of bananas was meant to be a visual aid to accentuate this effect. And indeed, my Kent State colleague, Tony Yockley, has done experiments with bent core liquid crystals, and he finds they have an especially big flexoelectric effect, bend flexoelectric effect. But it's not, the banana shape is not a necessary feature, right? So as long as the molecules have some complicated shape, they're not just featureless rods, that you'll get something like this.
So the curvature we are referring to is basically the deformation we are applying?
Yes, so you apply a deformation and you'll get this kind of extra ordering response.
Okay.
Mm-hmm. Great, great. Sean.
So in the chiral case, the previous page, is that coefficient somehow related with the twisting power of the chiral molecules you add into the system?
Right now I'm visualizing something that is initially achiral, and then you force a twist, right? And that induces some bias distribution. I imagine that the same effect would be related to what you're speaking about. That is, you put chiral molecules into an achiral system. That's kind of the next thing I'm going to say. So yes, so sort of as Shuang was just suggesting, let's do it all backwards, right? So here, this is what I've done so far, right? In my table, I'm filling in, there's some molecular order that couples to each of these deformations, okay? Now, I want to go backwards. Suppose you have a system that has a natural tendency to make some kind of extra molecular order, so that it's not just pneumatic, but it's pneumatic plus a little bit extra. I'll call it n plus epsilon, right? A little bit more than pneumatic, super pneumatic. All right, and then what will it do? Okay, so for example, suppose you have something that has a natural tendency to align banana-shaped molecules in this way, so that they have extra polar order perpendicular to the director. Okay? In that situation, you will not have an ideal state with a uniform director. Instead, the ideal lowest energy state will have some bend in the director, right? Physical effects generally go both ways, right? If a bend makes polar order, then polar order makes a bend, okay? And so you would get the converse flexoelectric effect happening here, okay? And so this is a little bit of a calculation trying to minimize over these modes as if they are independent, and it would predict there's an optimal bend which is proportional to this polar order, and then the optimal splay and twist and delta are all equal to 0. Likewise with splay. Okay? If you have molecules shaped like pears, or even with a pear-like component to their shape, okay, then the ideal director configuration is no longer going to be uniform, but rather it will have a certain amount of splay proportional to the strength of this parallel polar order. So it would be a configuration like this with non-zero splay, 0 bend, 0 twist, 0 delta. Okay. Now I want to point out, this is a situation where I have the regular liquid crystal free energy with splay squared, twist squared, bend squared, and delta squared. Okay? And then there is something else, an extra term, which is linearly proportional to splay. This is what's analogous to the Helfrich spontaneous curvature term. That is, if you have a difference in populations between molecules pointing up and molecules pointing down, that difference induces a splay, right, of the director going outwards, and that's like inducing a mean curvature, right? Because as I told you before our break, right, that the mean curvature is like a splay, okay? And so this is an interpretation, the sort of liquid crystal interpretation of where does a Helfrich spontaneous curvature term come from. Okay. So that's now bend and splay. What about twist? Okay. Well, this now is something organic chemists do all the time, right? There's a huge industry of organic chemistry making chiral molecules to go into liquid crystal phases. Just a second. Making chiral molecules to go into liquid crystals, right? And in that situation, the enantiomeric excess of the molecules couples to twist of the liquid crystals, so that in the free energy there is a term linearly proportional to twist, and the ideal structure now has non-zero twist, zero bend, zero splay, zero delta. Okay? So this is a very common organic chemistry thing. This is also the thing that Schwang was asking about pretty much a few minutes ago, right? Of what if you dope an achiral liquid crystal with chiral molecules? That also would make a little bit of a linear term in twist. Menon, you had a question?
I have a question. I'm confused about so the piece that you, for example, the bend, the piece that you added now is odd in director, and it's in the free energy.
No, it's not. Okay, so for the bend case, right? The piece that I added, it has bend coupled with polar order, right? So polar order is some extra order besides the pneumatic, okay? So it's an extra vector perpendicular to the director, okay? And that couples with bend, which is even in the director, okay? Now, with splay, likewise, I have this Sn, right? The Sn is the splay vector. So Sn is even in the director, and that couples with polar order along the director, right? But it's right that it should be linearly proportional to polar order, because that really is a vector, right?
But it, and the S is even, and the P parallel also means, whereas the P perpendicular doesn't.
Right. Uh-huh. Another question, please.
Can you flip this around and somehow use these sorts of different modes to drive processes on your particles that are commensurate with these different modes? Like somehow change the geometry of the kind of constituents by like forcing like
I'm not sure. I think maybe we need a longer discussion to visualize more, so I can visualize more what you have in mind there. It sounds really interesting, yes. But let's talk some more in a little while. Right, splay, I told you about twist. Okay, so likewise with this delta mode, right, if you have molecules with this shape that I made up, and they tend to align in the plane perpendicular to the director, okay, then they're characterized by some octopolar order parameter that will couple with the director and make a saddle-like deformation, right? So that if you have this, molecules with this funny shape aligned in that way, then the director will tend to tip outwards like this and inwards like that. Okay? I have a speculation that this could be important for membranes also. Okay? And that the same way that the splay case has a polar order that's different, a difference between up and down induces a sum of the principal curvatures, right? So it tends to make a membrane make a shape like a sphere, okay? And I'm speculating that this kind of order of funny shaped objects like that would induce a difference of the principal curvatures and would induce membranes to make a saddle-like shape. But that is kind of work in progress and not quite ready for prime time. Okay. All right. So now, coming back to liquid crystals, not membranes. All right. For liquid crystals, right, in these 4 situations that I've shown you here, in each of those situations, there's something where you have an ideal local structure. The ideal local structure has one of the modes non-zero and 3 of the modes 0. Okay. So then you might ask, okay, that's the ideal bend, splay, twist, and delta, but is it possible, right? Is there actually any director field that has the ideal bend, splay, twist, and delta? Not just at one position, but everywhere in space, right? So I know what's the ideal local structure, but is it possible to put the ideal local structure everywhere in space? Okay. The answer to this question is no. Okay. And there has been many years of theoretical research have gone into that word no, which I don't want to really talk about here. Okay. But let me just highlight one of the things on this list, which is the work of Epifanio Virga in the middle. Okay. So what he demonstrated was that in 3D Euclidean flat space, that is the space in which we live, you can't have a pure, constant, non-zero amount of any one of these modes. Okay? The best you can do is to have some combination of twist and delta, that could be uniform, or you can have a uniform combination of bend, twist, and delta, and that's all, right? So other than that, there just isn't any set of any director configuration that has the ideal thing. Okay, this is a case of geometric frustration, right? A very general phenomenon which has been studied extensively by Greg Grayson here at UMass in many contexts and by other people also. So here is a liquid crystal version of that general phenomenon. Okay, so then you can say the liquid crystal is frustrated. It wants to have a certain set of deformation modes, but there isn't any director field that it can possibly make that has that set of director deformation modes. So what can the liquid crystal do? How does it minimize its free energy? In general, there are 2 possibilities. One possibility is the liquid crystal can fill space with an allowed combination of director deformation modes. So it can fill space with the mode that it wants plus some other mode that it doesn't really want, but it's willing to take it in order to get the mode that it wants. Alternatively, it can break up space into domains of the favored mode, which are separated by some kind of defects, places where the liquid crystal is greatly disrupted away from its ideal structure. Both of these things can actually happen. Let me show you. Okay, I want to begin with the case that's driven by chirality, because that's the most common situation. Okay? So, suppose that some chemist has made a liquid crystal out of chiral molecules. Okay? So the molecules really are different from their mirror images. Okay? And so, based on the story that I told you, 5 or 6 slides ago, there is a spontaneous tendency to make twist. Okay? So the ideal local structure has non-zero twist, 0 splay, 0 bend, and 0 delta. Okay. But there isn't any director field that has that set of twist, splay, bend, and delta. Okay. So one thing that the liquid crystal can do is to make a cholesteric phase. Okay. A cholesteric phase is the phase with the structure like that. Okay, this is a very common thing in chiral liquid crystals. Okay, it's a structure where the director is changing as a function of z. Right, so down low it's like this. As you go upwards, it turns around in a helix like that. Okay, and it keeps turning periodically as a function of z. Okay, it's uniform as a function of x and y. All right, that's what this picture is meant to show. Okay, and it could be represented mathematically as a director that looks like this: cos wave vector times z, sine wave vector times z, comma 0. Okay, we can calculate what are the director deformation modes associated with this. Okay, splay is 0, twist is non-zero, bend is 0, delta is non-zero. Okay, so here is a place where I suggest it's actually important to think about delta, right? Because if you didn't think about delta, you might think that the cholesteric has pure twist, but it doesn't. Okay, the cholesteric twist is different from pure twist. Pure twist is going around like this. It's twisting in all directions perpendicular to the director, and the cholesteric is only twisting in one direction perpendicular to the director, right? So this is single twist in contrast with double twist. That's one possibility, okay? This is the most common thing that chiral liquid crystals do. But another thing that chiral liquid crystals also sometimes do is to make a blue phase. Okay, so a blue phase is a more complicated kind of structure where there are double twist tubes. That is to say, tubes where the director does approximately this pure double twist. Not exactly, but pretty close. Okay, and that works going out a certain finite distance from the center of the tube. And then when you get too far out from the center, the structure gets messed up. And the director, and the deformation is no longer just double twist. Okay? And so you can get a structure that has a bunch of these tubes arranged in a cubic lattice. And it could be either a simple cubic lattice like this or a BCC lattice like that. Those things are called blue phase 1 and blue phase 2. And these tubes have to be separated by disclinations in the director, right? That is, there's no way to join up the director continuously between the tubes. So the director is well defined in most places, I just haven't drawn it, but right along the blue lines, these are singularities in the director. They're disclinations like I showed you yesterday. Okay, These things really form in the lab, right? I mean, they're not just constructs, okay? So, if you're a chiral liquid crystal, which will you do? Should you make a cholesteric phase or a blue phase, right? These are both perfectly reasonable things for a chiral liquid crystal to make. Okay. If you make a cholesteric phase, you get single twist everywhere. So it's a combination of twist and delta. Okay. If you make a blue phase, then you've got tubes of pure double twist, which are separated by these disclination lines. Okay. In both of these cases, you can have any amount of twist. So in both of these cases, you can have the ideal amount of twist. It's not as if one has more twist than the other. Either one can have any amount of twist. So that doesn't differentiate them. What distinguishes between them is what do you have to sacrifice in order to get that twist? Okay? What price do you have to pay? In the cholesteric phase, the price is you have to have a non-zero delta mode everywhere. That costs some energy proportional to K24. In the blue phase, you don't have to have the delta mode, but you have to have all these disclinations. And the disclinations have some core energy associated with the singularity right along the disclination. So, which is worse? Well, it depends on what's the disclination energy per unit length compared with K24, right? If the disclination energy is really high, better to make a cholesteric phase. If K24 is really high, better to make a blue phase. Okay? So that's how I would propose to think about the distinction between cholesteric phase versus blue phase. Okay? So in some sense, people have been talking about this distinction for many years. It goes back probably 40 years in research on blue phases. But people always in the past spoke about it as a situation where saddle splay was making a surface energy, and the disclinations were like internal surfaces. And so the saddle splay made a negative energy for all these internal surfaces. And it's not wrong. I mean, it's mathematically exactly the same as what I'm presenting right here. But it's a matter of storytelling, like I said before with membrane theory, right? You try to say what sort of story seems plausible to go along with the mathematics. And to me, this is a story that seems more intuitive. How am I doing on time, Sean? 5 more minutes? Okay. I have related stories about modulations that are driven by these other modes. I will just show you pictures, okay? So if there is perpendicular polar order perpendicular to the director, okay, then one thing that a liquid crystal can do is to make this twist bend phase. This is a phase where the director is going around in a helix, but it's not perpendicular to the helical axis. It's going around like this, okay? And this director field has a combination of bend and twist and delta, okay? And so it could be stable if bend is favorable, and the liquid crystal will pay a price with twist and delta, but maybe it's worth it. This has been studied experimentally and theoretically over the last 15 years or so. This is a relatively new thing in liquid crystal science. Alternatively, there are speculations that you could get something more complicated like this. Okay, a phase, say, with a domain of bend, and then a wall where the polar order gets random, and then a domain of the opposite bend, and another wall where the polar order gets random, and then that repeats. Or the domain walls could be arranged in a more complicated kind of way, like that. So those things would be driven by P perpendicular to the director. For P parallel to the director, the liquid crystal tends to have some splay. There's no way it can possibly do that uniformly, okay? But it can make a domain structure. And so there's this kind of domain structure that has been reported experimentally that has a domain of splay upwards, and then a wall, and then a domain of splay downwards, and another wall, and it repeats periodically as a function of one coordinate. Alternatively, I have some speculation that instead the domains could be arranged in a checkerboard, like this. Alternatively, you might get something that's more like a lattice of micelles, or a lattice of hedgehogs, like I told you about hedgehogs, right? A lattice of hedgehogs arranged periodically, as in this picture, okay? And finally, for the case of a modulation driven by octopolar order, right? So if you had a liquid crystal made of these sort of distorted tetrahedra, and you wanted to pack them together, one thing that they could do would be to make a cholesteric phase, right? Because they want to have the delta deformation mode. The cholesteric phase has the delta deformation mode. So they could make a cholesteric phase that would be randomly right-handed or left-handed, right? So it could be like an achiral mechanism for making a cholesteric, whoops, or they could make something more like the splay pneumatic phases that I showed you. This is all kind of speculation at this stage. Okay. So that makes my table, right? That if you have these different director deformation modes, they tend to induce molecular order in addition to pneumatic order. Or if you have these kinds of molecular order, they tend to make the director deformation modes, but it's just not possible to have pure director deformation modes. So the liquid crystal has to do some kind of compromise where it has some of the mode that it wants and maybe some of the mode that it doesn't want and maybe some walls in between. And my speculation is that this is why liquid crystals have so many phases, right? That there are just 4 things that the director field might want to do, but it can't actually achieve them, so it has to make all kinds of different compromises, and there are lots of possible ways to do that. So with that, I will close, and I thank you very much. Please. The disclination energy, like between the cholesteric and the blue phase. There are phase diagrams that have both of those things, and there's a first order transition between them. And so as you change temperature or other parameters, yes, you will go from one to the other. But it's a first order transition with hysteresis. Mm-hmm.
So before I let you go, let's, I think for this experiment of people crystal like me, I feel like just upgraded my operating system. For people who have not had, I hope you had a good journey with Jonathan, which is fantastic, I think. So let's give us another one.
Thank you, Swan.